Picture this. The African savannah stretches endlessly before you, bathed in the golden light of a setting sun 300,000 years ago. The air smells of dry grass and distant rain. A figure emerges on the horizon. At first glance, you might mistake this silhouette for a modern human. The straight posture, the balanced stride, the distinctive shape of the skull. But you'd be witnessing something profound. One of the first members of our species taking steps across the ancient Earth. These early Homo sapiens, our direct ancestors, walked the planet in a time almost beyond comprehension. They inhabited a world we would barely recognize, yet carried within them the fundamental blueprint of humanity that defines us today. The mystery that has puzzled scientists for generations is this: when exactly did we become us? When did our species truly emerge with the cognitive capabilities, social structures, and physical traits that we recognize as quintessentially human? Traditional timelines placed modern humans emerging around 200,000 years ago, but recent discoveries have shattered this timeline, pushing our origins back by at least another 100,000 years, a revelation that fundamentally changes our understanding of human history. Fossilized remains discovered in Morocco at Jebel Irhoud tell us something remarkable. Anatomically modern humans existed far earlier than we thought. These weren't our evolutionary cousins or distant relatives. These were people like us walking the earth 300,000 years ago. Their brain cases showed the distinctive globular shape of modern humans. Their faces already displayed the flatter profile characteristic of our species, distinct from more robust earlier hominins. These weren't transitional forms, they were us. What's most perplexing is what this means for human development. If our species emerged 100,000 years earlier than previously believed, why did it take so long for complex culture, art, and advanced tools to appear in the archaeological record? This documentary explores the profound mystery at the heart of human origins. How did these earliest members of our species live? What did they think? How did they survive? And most importantly, what happened during those missing 100,000 years of human development? We'll journey through African savannas, where human consciousness first flickered to life. We'll examine ancient fossil beds that contain the fragmentary remains of our earliest ancestors, piecing together their stories from the impressions left in stone. We'll walk alongside paleoanthropologists as they uncover new evidence that rewrites our understanding of ourselves. We'll analyze cutting-edge genetic data that reveals surprising connections across time and geography, painting a picture of ancient human migrations. The story of early humans is not just academic curiosity, it's the story of us. Understanding our origins gives profound insight into who we are today, why we behave as we do, and perhaps most importantly, what makes us uniquely human. Throughout this journey, we'll confront competing theories that attempt to explain the puzzling gap between anatomical modernity and behavioral modernity. We'll explore the possibility that advanced human behavior emerged much earlier than the archaeological record suggests. We'll examine controversial evidence of sophisticated tool use, potential symbolic thinking, and early social structures that may have existed far earlier than conventionally thought. We'll consider whether the absence of evidence truly represents evidence of absence. By the end of this documentary, you'll have a new perspective on human origins, one that challenges conventional wisdom and opens exciting possibilities about our ancient past. You'll understand why recent discoveries have sent shockwaves through the scientific community. This is more than just prehistory. It's your prehistory, the story of your earliest ancestors and the world they inhabited. It's a story written in fossils, stones, and DNA, waiting to be decoded and understood. So join us as we travel back 300,000 years to meet the first humans who walked like us. Let's discover together how these ancient people lived, what challenges they faced, and how they set humanity on its extraordinary path. The journey into our deep past begins now. The mystery of those first true humans awaits us. Let's step back in time and meet our most ancient selves. Tonight, we unravel the enigma of humanity's dawn, a story far older, stranger, and more complex than we ever imagined. The evidence will challenge everything you thought you knew about what it means to be human. As we begin this exploration, keep one question in mind. What truly makes us human? Is it our biology, our behavior, our capacity for symbolic thought? Or is it something more elusive that emerged gradually over thousands of generations? Chapter 2. Premise and Stakes. 300,000 years ago, a momentous event occurred on the African continent. An event lost to direct memory, yet inscribed in our very bones. The emergence of anatomically modern humans fundamentally changed the trajectory of life on Earth in ways unimaginable to those earliest members of our species. These first Homo sapiens stood at the threshold of humanity's journey. Their existence poses profound questions about the nature of human development and challenges our understanding of what it means to be fully human, in both biological and behavioral terms. The stakes of this investigation reach far beyond academic curiosity. How we understand our origins shapes how we view ourselves as a species, influencing everything from our sense of connection to the natural world to our vision of humanity's future. If these earliest Homo sapiens possessed the same cognitive capabilities as modern humans from the beginning, why did it take nearly 100,000 years for complex culture, art, and technology to emerge? This paradox has been termed the sapiens paradox by researchers. Conventional wisdom suggested a gradual development of human capabilities, with anatomical modernity preceding behavioral modernity by tens of thousands of years. But what if this model is wrong? What if the absence of evidence simply reflects preservation bias? The implications would be revolutionary. We would need to reimagine those first 100,000 years not as a period of cognitive stasis, but as a complex era of human development whose traces have been largely erased by time. Consider the alternative. Perhaps the earliest anatomically modern humans did not possess the same cognitive architecture as later populations. Perhaps crucial neural reorganization occurred after anatomical modernity, eventually giving rise to the fully symbolic mind. This would suggest that looking modern and being cognitively modern are separate evolutionary developments. It would mean that the special human capacity for abstract thought, art, and complex language emerged more recently than our physical form. Either possibility forces us to reconsider fundamental questions about human uniqueness. What truly sets us apart from other species? When did the human mind as we know it today truly emerge? How gradual or sudden was this transformation? These questions touch on the very essence of our humanity. They prompt us to consider what aspects of ourselves we share with those ancient people who looked like us, but lived in a world so different from our own. The temporal gap between anatomical modernity and the first clear evidence of symbolic behavior challenges us to reconsider the archaeological record. Perhaps evidence of cognitive complexity exists, but has gone unrecognized or has simply not survived the passage of time. Recent discoveries provide tantalizing hints that behavioral modernity may indeed have emerged earlier than previously thought. Engraved ochre pieces from Blombos Cave in South Africa, dating to 75,000 years ago, suggest abstract thinking far earlier than once believed. Shell beads found at sites like Tafaralt in Morocco and Kafse in Israel indicate personal adornment, a distinctly human behavior, at least 80,000 years ago. These discoveries push back the timeline for symbolic thinking, but still leave a substantial gap. What if we're simply looking for the wrong evidence? Perhaps these earliest humans expressed their cognitive complexity in ways that haven't preserved, using organic materials that decomposed long ago, or creating ephemeral art forms that left no trace. If we discover that complex human behavior emerged alongside anatomical modernity 300,000 years ago, we would need to completely rewrite our understanding of human history. The implications would extend to every aspect of paleoanthropology. The geographic origins of our species would need reconsideration as well. The Jebel Irhoud findings in Morocco suggest that early Homo sapiens were present across Africa, not just in the eastern regions as previously believed. This Pan-African model of human origins suggests a more complex pattern of evolution and migration than the simple out of East Africa narrative. Our species may have emerged through interconnected populations across the African continent, sharing innovations through contact and gene flow. The stakes extend to how we understand human diversity today. If modern humans evolved across Africa in a complex network of populations rather than from a single source population, it changes how we interpret the genetic diversity present in living humans. It would mean our species has been characterized by population connectivity and genetic exchange from its very beginning. This understanding could help dismantle outdated notions of distinct human races by highlighting the fundamental interconnectedness of all human populations. Beyond scientific implications, this investigation touches something deeply personal in all of us: our need to understand our origins. Humans across cultures have created origin stories that give meaning to our existence and place in the natural world. Science provides its own origin story, one written in fossils and DNA rather than myth. But this story is continuously evolving as new evidence emerges, reminding us that our understanding of ourselves is never complete. If we discover that human cognitive potential emerged fully formed 300,000 years ago, it would suggest that our species possessed extraordinary capabilities from its very beginning. It would mean that the same minds that eventually built civilizations were present at our dawn. Conversely, if we confirm that cognitive modernity developed gradually over tens of thousands of years after anatomical modernity, it offers a different perspective on human potential. It suggests that our species underwent a prolonged childhood before reaching its full capabilities. Either way, the stakes of this investigation involve our deepest questions about ourselves. Who are we as a species? What is our relationship to our ancient past? And what does it mean to be human in the fullest sense? As we explore the evidence for early human capabilities, we'll consider how environmental pressures, social structures, and technological innovations may have shaped cognitive development. We'll examine how survival challenges may have sparked crucial adaptations in human thinking. We'll also investigate how changing climates during this period may have influenced human evolution. Did severe environmental stresses create evolutionary bottlenecks that accelerated cognitive development? Or did relatively stable periods allow cultural innovations to flourish? The quest to understand our earliest ancestors is ultimately a quest to understand ourselves. By the end of this investigation, we'll have a clearer picture of where we came from, how we developed our unique human qualities, and what that reveals about our shared humanity. What we discover about these first members of our species will change how you see the modern world. It will transform your understanding of human potential and the extraordinary journey that brought our species to the present moment. As we continue, remember that each fossil fragment, stone tool, and genetic marker we examine brings us closer to answering the fundamental question: what does it truly mean to be human? And when did we first become the creatures we recognize as ourselves? Chapter 3: Historical Context. To understand the significance of the first anatomically modern humans, we must first place them in the broader context of human evolution. Our story begins not 300,000 years ago, but millions of years earlier, when the first hominins diverged from other primates. Approximately 7 million years ago, the evolutionary lines leading to humans and chimpanzees separated. From this divergence emerged the first hominins, upright walking primates that would eventually lead to our species. Early hominins like Sahelanthropus chadensis and Ardipithecus showed the first experiments with bipedalism while retaining ape-like features. They represent our first steps, literally, toward becoming human, though they would be unrecognizable to us today. By about 4 million years ago, the Australopithecines had appeared. These more clearly bipedal hominins, including the famous Lucy, Australopithecus afarensis, walked upright, but had relatively small brains and ape-like proportions. The emergence of the genus Homo around 2.8 million years ago marked a significant shift. These early humans had larger brains, made stone tools, and began the adaptive patterns that would eventually lead to our species. Homo habilis, the handyman, created the first recognizable stone tools around 2.6 million years ago. These Oldowan tools, simple choppers and flakes, represent the dawn of human technology, though they remained unchanged for nearly 1 million years. Homo erectus appeared around 1.9 million years ago, bringing revolutionary changes. With a larger brain, more modern body proportions, and control of fire, Homo erectus became the first hominin to leave Africa and spread across much of the Old World. For over 1 million years, Homo erectus and related species like Homo heidelbergensis thrived across Africa and Eurasia. They developed more sophisticated Herculean tools, including the distinctive teardrop-shaped hand axes that remained in use for over 1 million years. This remarkable technological stability suggests that while these species were intelligent toolmakers, they lacked the rapid cultural innovation that characterizes modern humans. Their technology evolved over geological timeframes rather than generations. The Middle Pleistocene, roughly 780,000 to 130,000 years ago, saw increasing complexity in the human evolutionary tree. Multiple hominin species coexisted, including Neanderthals in Europe, Denisovans in Asia, and the mysterious Homo naledi in South Africa. It was in this diverse evolutionary landscape that Homo sapiens emerged, not as a sudden appearance, but through a complex process of evolution across the African continent, with populations connected through migration and genetic exchange. The traditional narrative placed modern human origins around 200,000 years ago in East Africa, based primarily on fossils from Ethiopia's Omo Kibish Formation. This out-of-East Africa model suggested a relatively straightforward evolutionary story. But the 2017 redating of fossils from Jebel Irhoud in Morocco to 315,000 years ago dramatically changed this picture. These remains, with their modern-looking faces and expanded brain case, pushed back the origin of our species by over 100,000 years. Just as importantly, their location in North Africa challenged the East African origin story. It suggested that early Homo sapiens were already widespread across Africa, indicating a more complex evolutionary history than previously thought. The Jebel Irhoud individuals weren't identical to modern humans. Their brain case was elongated rather than globular, and certain primitive features remained. But they were unmistakably on the Homo sapiens lineage, representing an early form of our species. Other fossil evidence supports this extended timeline and Pan-African origin. Remains from Herto and Omo Kibish in Ethiopia, dating to 160,000 to 180,000 years ago, show features intermediate between the Jebel Irhoud fossils and later fully modern humans. The climate during this critical period fluctuated dramatically. Between 350,000 and 300,000 years ago, Africa experienced severe dry periods alternating with wetter phases, creating a dynamic environment that may have driven human adaptation and innovation. These climate shifts fragmented habitats, potentially isolating populations and accelerating evolutionary change. When conditions improved, these populations could reconnect, sharing beneficial genetic adaptations and cultural innovations. This pattern of isolation and reconnection likely played a crucial role in human evolution. Rather than a linear process, our emergence appears to have been reticulated, a complex network of populations exchanging genes and ideas across the African continent. Genetic evidence supports this model of interconnected populations. Studies of both ancient DNA and modern human genetic diversity suggest that our species arose through a complex process involving multiple populations across Africa. Around 300,000 years ago, major technological transitions were also occurring. The simpler Herculean toolkit was giving way to Middle Stone Age technologies, which included more sophisticated prepared core techniques for creating stone tools. The Levallois technique, which allowed toolmakers to predetermine the shape of stone flakes, represented a significant cognitive advance. It required abstract thinking and planning several steps ahead, hallmarks of modern human cognition. Interestingly, the Jebel Irhoud site contained Middle Stone Age tools made using this advanced technique. This suggests that technological innovation and anatomical modernity were emerging together, though full behavioral modernity would come later. Fire use was well established by this time, with evidence of controlled burning at numerous sites, The mastery of fire provided warmth, protection, and allowed for cooking, which may have contributed to brain development through improved nutrition. Early humans were primarily hunter-gatherers, living in small mobile groups. They followed seasonal resources across landscapes that were often quite different from today's environments due to climate fluctuations. The African savanna during this period teemed with now extinct megafauna. Giant buffalo, massive elephants, and large predators created a challenging environment that would have required sophisticated hunting strategies and social cooperation. These early Homo sapiens weren't solitary hunters. They lived in interconnected social groups. Their survival depended on cooperation, communication, and the transmission of knowledge across generations. Evidence suggests they occupied diverse habitats across Africa, from coastal regions to inland savannas and forests. This ecological adaptability would become one of our species' defining characteristics, eventually allowing humans to colonize virtually every environment on Earth. Language capabilities at this stage remain uncertain. While these early humans possessed the anatomical structures necessary for speech, we cannot know when complex language emerged. The capacity for symbolic communication likely developed gradually. What we can say with certainty is that these earliest members of our species were on the cusp of something extraordinary. They stood at the threshold of becoming fully modern in both body and mind, though this process would unfold over many thousands of years. Their world was fundamentally different from ours, Africa teeming with multiple human species, enormous beasts, and landscapes alternately parched by drought and transformed by abundant rainfall. Yet they carried within them the blueprint of humanity's future. As we've established the historical context, a crucial question emerges. What evidence do we have of these first anatomically modern humans? What fossils, artifacts, and sites reveal their presence and capabilities? And what do these findings tell us about who they were? Chapter 4: First Evidence. The story of the first anatomically modern humans begins with fragments, literal fragments of bone and stone that have survived the immense passage of time. These precious remnants offer glimpses into a pivotal moment in human evolution, when our species first appeared. The most compelling evidence comes from Jebel Irhoud, Morocco, a site that has revolutionized our understanding of human origins. Discovered in the 1960s, these fossils were initially thought to be around 40,000 years old and classified as African Neanderthals. Subsequent analysis suggested they were older, perhaps 160,000 years, but still well within the conventional timeline for Homo sapiens. Then, in 2017, a breakthrough occurred that would upend our understanding of human evolution. Using advanced dating techniques, scientists from the Max Planck Institute determined that the Jebel Irhoud fossils were actually 315,000 years old. This stunning revision pushed back the origin of our species by more than 100,000 years. The Jebel Irhoud remains include partial skulls, a mandible, and assorted postcranial elements from at least 5 individuals. These fossils show a fascinating mixture of archaic and modern features that provide crucial insights into human evolution. The faces of these individuals would have been strikingly familiar, with relatively flat profiles, smaller brow ridges, and overall proportions similar to modern humans. Yet their brain case was more elongated than ours, lacking the distinctive globular shape of later Homo sapiens. This combination suggests that modern human features evolved in a mosaic pattern rather than all at once. The face evolved modern characteristics before the brain case achieved its final form, challenging simplistic linear models of human evolution. CT scans of the Jebel Irhoud skulls reveal fascinating details about brain organization. While their brains were similar in size to modern humans, the shape difference suggests some aspects of brain organization were still evolving. The globular brain case of fully modern humans accommodates expanded parietal lobes and cerebellum, areas associated with complex cognition, visual imagery, and procedural memory. The more elongated shape of the Jebel Irhoud crania suggests these regions were less developed. This difference may be crucial for understanding when fully modern cognition emerged. Brain shape, more than size alone, appears to correlate with the cognitive capabilities that define behavioral modernity. The site also yielded abundant stone tools, made using the sophisticated Levallois technique. This advanced method requires planning and spatial visualization. The toolmaker must envision the final product within the stone before beginning work. The presence of these tools alongside the earliest Homo sapiens fossils suggests cognitive capabilities were already advancing. These weren't simple tools. They required abstract thinking and the ability to teach complex skills across generations. Evidence of controlled fire use was also present at Jebel Irhoud. Many of the stone tools show signs of heat treatment, a technique that improves flaking quality. This demonstrates sophisticated understanding of how materials can be transformed. Remains of gazelles, zebras, and other savanna animals found at the site reveal hunting behaviors. Cut marks on these bones show these early humans were skilled at butchering game, suggesting well-developed subsistence strategies. Beyond Jebel Irhoud, other sites have yielded fossils that help piece together the story of early Homo sapiens. Remains from Florisbad in South Africa, dated to approximately 260,000 years ago, show a similar mixture of archaic and modern features. The Florisbad skull, though fragmentary, exhibits a face more similar to modern humans than to earlier hominins. Its discoverers classified it as archaic Homo sapiens, recognizing it as transitional between earlier forms and fully modern humans. At Herto in Ethiopia, 3 partial skulls dated to approximately 160,000 years ago represent a slightly later stage in human evolution. These individuals had more modern features than the Jebel Irhoud fossils, though still retaining some archaic characteristics. The Herto remains were classified as Homo sapiens idaltu, a subspecies of our own species that represents an intermediate form. Their brain case was more globular than at Jebel Irhoud, suggesting the reorganization of the brain was progressing. Intriguingly, the Herto skulls show evidence of cultural practices. Cut marks suggest deliberate defleshing after death, possibly representing mortuary rituals. If so, this would be early evidence of symbolic behavior, though its meaning remains unclear. Genetic evidence complements these fossil findings. Analysis of both modern human DNA and limited ancient DNA suggests that our species emerged through a complex process of population divergence, isolation, and reconnection across Africa. The latest genetic models suggest that Homo sapiens emerged from a Pan-African network of populations connected by intermittent gene flow. Rather than a simple origin in one region, our species appears to have evolved across the continent. This genetic evidence aligns with the fossil record showing early Homo sapiens in both North Africa, Jebel Irhoud, and East Africa, Herto. It suggests multiple populations were evolving in parallel, exchanging genes when climate conditions permitted contact. Archaeological evidence from this period shows technological advancement across Africa. The transition from earlier Stone Age, Acheulean, to Middle Stone Age technologies was occurring, with more sophisticated tools appearing in multiple regions. Sites like Katanda in the Democratic Republic of Congo have yielded barbed bone points dating to approximately 90,000 years ago. These sophisticated hunting implements represent advanced technology, requiring complex manufacturing processes and specialized knowledge. At Blombos Cave in South Africa, archaeologists discovered 75,000-year-old ochre pieces engraved with geometric patterns. These markings appear deliberately symbolic rather than functional, potentially representing early artistic or notational systems. Shell beads found at sites including Blombos Cave, Kafze in Israel, and Tafaralt in Morocco date from 70,000 to 100,000 years ago. These personal ornaments suggest symbolic thinking and social signaling, key components of behavioral modernity. The geographic distribution of these findings is significant. Evidence of early anatomically modern humans and increasingly sophisticated behavior appears across Africa, supporting the model of a continent-wide emergence of our species. The archaeological record becomes increasingly rich after 100,000 years ago, with more abundant evidence of complex behavior. This raises a critical question. Does this represent the actual emergence of these behaviors, or simply better preservation of more recent material? This brings us to the central mystery. If anatomically modern humans existed 300,000 years ago, why did it take so long for clear evidence of modern behavior to appear? This gap between anatomical and behavioral modernity is the puzzle at the heart of our investigation. Several possibilities might explain this paradox. Perhaps early modern behaviors did exist, but left little archaeological trace, particularly if they involved organic materials that rarely preserve over such vast timeframes. Alternatively, anatomical modernity might have preceded cognitive modernity. Perhaps the neural reorganization necessary for fully modern behavior developed gradually over thousands of generations after our species first appeared. A third possibility is that modern behavior emerged early but remained sporadic and localized until population increases and better connectivity allowed innovations to spread and persist. Small, isolated populations might have repeatedly developed and lost complex behaviors. Evidence supporting this third hypothesis comes from sites like Pinnacle Point in South Africa. Here, researchers found evidence of advanced behaviors appearing, disappearing, and reappearing over thousands of years, suggesting innovations could be lost during population bottlenecks. As we examine these possibilities, a startling new discovery has recently emerged that may change everything we thought we knew about early human capabilities. Evidence that has remained hidden until now suggests our ancestors may have been far more advanced than previously believed. In a remote cave system recently excavated in southern Africa, archaeologists have uncovered artifacts that defy conventional understanding. The findings are preliminary, but if confirmed, they could revolutionize our conception of early human cognitive abilities. The site, which we'll explore in detail in the next section, contains evidence dating to approximately 250,000 years ago, well within the time frame of early Homo sapiens. But what makes this discovery extraordinary is the nature of the artifacts themselves. Unlike the simple stone tools typical of this period, these findings suggest symbolic thinking and social complexity far earlier than conventionally accepted. They hint at capabilities previously thought to have emerged only in the last 100,000 years. The team of researchers who made this discovery have remained cautious, subjecting their findings to rigorous analysis before publishing. Dating techniques are being cross-verified and alternative explanations carefully considered. But if their preliminary conclusions prove correct, we may need to entirely reconsider the timeline of human cognitive evolution. The gap between anatomical and behavioral modernity might be an illusion, a result of preservation bias rather than actual historical reality. What exactly was found in this mysterious cave system? What does it tell us about the minds of the first humans who walked like us? And why has this evidence remained hidden for so long? The answers to these questions could fundamentally transform our understanding of human origins. They might reveal that our ancestors possessed remarkable capabilities far earlier than we ever imagined, rewriting the story of what it means to be human. As we prepare to examine this extraordinary new evidence in detail, we must consider what it would mean if early Homo sapiens were indeed capable of complex symbolic thought and social organization from the beginning. It would challenge everything we thought we knew about human evolution. The mystery deepens, and the story of humanity's dawn becomes more complex. What secrets have remained hidden in the shadows of our ancient past, and what will they reveal about who we truly are? Chapter 5. Contradictions and Anomalies. The conventional narrative of human origins has always contained contradictions, puzzling gaps in the timeline that challenge our understanding. As we dig deeper into the evidence, these anomalies become increasingly difficult to explain away through traditional models. Consider the site of Olorgesailie in Kenya, where archaeologists discovered sophisticated tools dating to 320,000 years ago. These included small, carefully crafted obsidian blades that required not only advanced technical skill, but complex trade networks to acquire the raw material. The obsidian used in these tools originated from sources up to 90 kilometers away. This indicates trade or resource acquisition over distances that suggest sophisticated social organization far earlier than traditionally accepted models of human development. Even more surprising was the discovery of red and black pigments at the same site. These minerals had no obvious utilitarian purpose, suggesting they may have been used for body decoration or other symbolic purposes hundreds of thousands of years ago. If correct, this evidence contradicts the notion that symbolic behavior emerged only within the last 100,000 years. It suggests that early Homo sapiens were engaging in complex social and potentially symbolic behaviors from the very beginning of our species. At Jebel Irhoud, the site that pushed back human origins to 315,000 years ago, additional contradictions emerge. The sophisticated stone tools found there were made using the Levallois technique, which requires abstract visualization and planning. This advanced cognition seems at odds with the slightly archaic brain shape of these early humans. If their cognitive abilities were sophisticated enough for advanced tool production, why doesn't their brain morphology match that of modern humans? One possibility is that neural organization, not just brain shape, enabled these cognitive capabilities. Perhaps the pathways for complex thinking were already present, even as the overall brain structure continued to evolve toward its modern configuration. Another contradiction emerges when we consider cave art and symbolic expression. The earliest widely accepted cave paintings date to approximately 40,000 years ago in Europe, suggesting that symbolic expression emerged relatively late in human evolution. However, recent discoveries have challenged this timeline. Cave art in Indonesia has been dated to at least 45,500 years ago and possibly much older, indicating that symbolic art may have originated long before its appearance in Europe. Even more remarkable, abstract engravings discovered in South Africa's Blombos Cave date to 73,000 years ago. These geometric markings on ochre pieces suggest symbolic thinking far earlier than previously thought. But even these discoveries leave a substantial gap between the emergence of anatomically modern humans 300,000 years ago and the first clear evidence of symbolic behavior. This contradiction forces us to question whether we're seeing the true beginning of such behaviors or merely their preservation. The archaeological record presents another puzzle: periods of apparent technological stasis interrupted by sudden innovation. The Acheulean hand axe tradition persisted with little change for over 1 million years, suggesting minimal cultural evolution. Yet the transition to Middle Stone Age technologies around 300,000 years ago shows relatively rapid innovation. This pattern of long stability, punctuated by periods of change, doesn't match our understanding of how human cultural evolution typically proceeds. Perhaps the most perplexing contradiction involves the timing of the Great Leap Forward, the apparent explosion of cultural and technological innovation that appears in the archaeological record around 40,000, 50,000 years ago. This period saw an unprecedented flourishing of art, complex tools, and evidence of ritual behavior. This sudden acceleration of cultural complexity has traditionally been attributed to a cognitive or genetic change that enhanced human capabilities. Yet the physical evidence shows that anatomically modern humans existed long before this cultural revolution. Some researchers have proposed a genetic mutation affecting language or symbolic thought may have occurred around this time. However, genetic evidence has failed to identify any such dramatic change in the human genome during this period. An alternative explanation suggests that the apparent leap was actually the culmination of gradual developments that finally reached a tipping point. Small innovations accumulated over thousands of generations until they produced dramatic cultural change. Yet this explanation struggles to account for the relative lack of evidence for gradual symbolic development in the preceding periods. If symbolic thought was developing incrementally, we would expect to find increasingly complex examples as we approach the Upper Paleolithic period. The anomalies extend to human migration patterns as well. Traditional models placed the exodus of Homo sapiens from Africa around 60,000 years ago, with all non-African populations descending from this migration. However, fossil discoveries have repeatedly contradicted this timeline. Modern human remains found in Israel's Mislia cave date to 185,000 years ago, while those from Apodema cave in Greece have been dated to 210,000 years ago. These findings suggest that Homo sapiens ventured out of Africa much earlier and more frequently than previously thought. Yet these early migrations apparently failed to establish permanent populations, raising questions about why later migrations succeeded where earlier ones failed. Even more puzzling are the recent discoveries in China. Fossils from Fuyan Cave have been dated to between 80,000 and 120,000 years ago, while those from Dioxean might be as old as 125,000 years. These dates precede the supposed main exodus from Africa by tens of thousands of years. They suggest either multiple successful migrations or a much earlier primary dispersal of modern humans from Africa. Genetic evidence presents its own contradictions. Analysis of modern human DNA suggests that all non-African populations descended from a migration around 60,000 years ago, yet the fossil evidence indicates modern humans were present in Asia and Europe much earlier. This apparent contradiction might be resolved if earlier migrations left no genetic legacy in current populations. Perhaps these pioneering groups died out completely, replaced by later waves of migrants from Africa. But this raises yet another question. Why would multiple early migrations fail, while later ones succeeded? What changed to allow modern humans to finally establish permanent populations outside Africa after 60,000 years ago? The archaeological record contains other anomalies that challenge conventional understanding. At the site of Pinnacle Point in South Africa, evidence suggests humans were collecting and cooking shellfish by 164,000 years ago, far earlier than previously recognized. This behavior requires understanding tidal patterns and the nutritional value of marine resources. It suggests cognitive capabilities for recognizing patterns in nature and planning resource acquisition based on natural cycles. Perhaps most anomalous are the increasing indications of symbolic behavior predating the Upper Paleolithic Revolution. Perforated shell beads from sites across North Africa and the Levant date to 100,000, 135,000 years ago. These personal ornaments, likely used for bodily decoration, imply social signaling and symbolic communication. Their presence contradicts the notion that symbolic behavior emerged suddenly around 40,000 years ago. Burial practices provide further contradictions. Intentional burials at sites like Kafse and Skul in Israel date to approximately 100,000 years ago, suggesting ritual behavior and possibly belief in an afterlife. Some of these burials included items like deer antlers and red ochre, hinting at symbolic meaning. These practices appear tens of thousands of years before the supposed emergence of complex symbolic behavior. The Neanderthal question presents another set of anomalies. Long considered intellectually inferior to Homo sapiens, evidence now suggests they created symbolic art, buried their dead ritually, and manufactured complex tools. If Neanderthals, who diverged from our lineage hundreds of thousands of years ago, independently developed symbolic capabilities, it raises the possibility that the cognitive foundation for such behaviors was present in our last common ancestor. This would push the potential for symbolic thought back at least 500,000 years. Another contradiction emerges from the study of language capabilities. The FOXP2 gene, associated with language in humans, appears to have undergone selection around 100,000 to 200,000 years ago, suggesting language might have emerged during this period. Yet anatomical evidence, including the hyoid bone necessary for modern speech, indicates that the physical capability for complex vocalization existed in Homo heidelbergensis at least 400,000 years ago. This suggests the potential for language long before modern humans evolved. All these contradictions and anomalies point to a fundamental problem with our understanding of early human cognitive evolution. The timeline doesn't make sense if we assume a gradual, linear progression from anatomical modernity to behavioral modernity. Either modern human behavior is much older than the archaeological record suggests, or the relationship between anatomy and behavior is far more complex than we've assumed. In either case, our understanding of what makes us human requires significant revision. As we continue our exploration, these contradictions will deepen. The evidence ahead challenges not just the timeline of human evolution, but our very conception of what constitutes humanity. The mystery grows more complex and more fascinating. Chapter 6. Myths and out-of-place evidence. Throughout human history, myths and legends have preserved memories of our distant past, stories that, while embellished over time, may contain kernels of truth about our origins. These narratives, found across cultures worldwide, often describe a time when humans possessed knowledge or abilities that were subsequently lost. Creation myths frequently describe humans as being formed in the image of gods, or emerging fully formed with capabilities similar to modern humans. While these are religious concepts, they align intriguingly with the scientific evidence showing that anatomically modern humans appeared relatively suddenly in the fossil record. Consider the San people of southern Africa, whose genetic lineage represents one of the oldest in the human family tree. Their creation myths describe the first humans as possessing knowledge that was later forgotten, preserved only in fragments by shamanic traditions. Similarly, Aboriginal Australian Dreamtime stories speak of ancestral beings who possessed knowledge of the world that was gradually lost. These stories emphasize continuity with ancient ancestors rather than a narrative of progressive improvement over time. These mythological frameworks stand in contrast to the scientific model of gradual cognitive evolution. They suggest instead that knowledge and capabilities might have been possessed by early humans but subsequently fragmented or lost during population bottlenecks. While mythology cannot be considered empirical evidence, it raises an intriguing possibility. Could early human populations have developed complex cultural knowledge that was later lost? This would align with both the mythological record and the archaeological contradictions we've examined. This possibility becomes more compelling when we consider certain out-of-place archaeological findings, evidence that seems anomalous within conventional chronologies of human development. These findings hint at capabilities that conventional models suggest shouldn't have existed at such early dates. Among the most intriguing out-of-place evidence are the recent discoveries at Guanyindong Cave in China. Here, archaeologists found sophisticated stone tools dating to approximately 170,000 years ago, made using techniques previously thought to have emerged much later. These tools show evidence of platform preparation, a technique requiring advanced planning and precise control. Their presence suggests that the cognitive capabilities for such sophisticated stoneworking existed far earlier than conventionally thought. At Border Cave in South Africa, researchers discovered what appears to be the earliest known example of a wooden tool, a carefully shaped digging stick dating to 40,000 years ago. While this doesn't seem particularly ancient, the preservation of wooden artifacts is extremely rare. This raises a compelling question. If wooden technology was already sophisticated 40,000 years ago, how much earlier might humans have been creating such tools? The answer might forever remain unknown, as wood simply doesn't preserve over hundreds of thousands of years. This preservation bias creates a fundamental problem in archaeological interpretation. We can only study what has survived, and materials like wood, fiber, and animal hide, which likely constituted the majority of early human material culture, rarely preserve in the archaeological record. Consider that modern hunter-gatherer groups typically possess hundreds of distinct tool types, yet stone tools make up only a small percentage of their total toolkit. If the same was true of ancient humans, we may be missing the vast majority of their technological achievements. The absence of evidence becomes particularly problematic when considering symbolic behavior. Body painting, storytelling, dance, and music would leave little or no archaeological trace, yet these might have been central to early human cognitive and cultural life. Certain anomalous findings hint at this possibility. A 115,000-year-old shell from Kafza Cave shows evidence of being painted with red ochre, suggesting symbolic use of color far earlier than traditionally accepted. At Kathupan in South Africa, archaeologists discovered what appears to be an advanced hunting technology, stone points likely used as spear tips, dating to 500,000 years ago. This suggests sophisticated hunting strategies among Homo heidelbergensis, long before Homo sapiens evolved. The site of Schöningen in Germany yielded wooden spears dated to approximately 300,000 years ago. These perfectly balanced throwing spears, likely created by Homo heidelbergensis, demonstrate woodworking skills and hunting capabilities previously thought to have emerged much later. Perhaps most remarkable are the findings from Bruniquel Cave in France. Deep within this cave, archaeologists discovered circular structures built from broken stalagmites, dated to an astonishing 170–6,500 years ago, a time when only Neanderthals inhabited Europe. These structures, located 336 meters from the cave entrance in complete darkness, suggest not only control of fire for illumination, but symbolic or ritual behavior among Neanderthals. This undermines the notion that such behaviors were unique to Homo sapiens. If Neanderthals were capable of such behaviors, it seems increasingly likely that the common ancestor of Neanderthals and modern humans possessed the cognitive foundations for symbolic thought. This would push the capacity for such behaviors back to at least 500,000 years ago. Other out-of-place findings include potential evidence of seafaring. Stone tools discovered on the island of Crete have been dated to at least 130,000 years ago, a time when the island was already separated from the mainland by significant stretches of open water. To reach Crete, early humans would have needed watercraft and navigation abilities. This suggests maritime capabilities far earlier than the conventional timeline, which places the first definitive evidence of seafaring at around 50,000 to 60,000 years ago. Similarly, the presence of humans in Australia by at least 65,000 years ago required sea crossings of up to 90 kilometers. Even with lower sea levels during glacial periods, reaching Australia necessitated multiple sea voyages beyond the visible horizon. These maritime achievements suggest sophisticated capabilities for planning, constructing watercraft, and navigating open water. Such abilities seem at odds with the conventional view of gradual cognitive evolution, culminating only 40,000, 50,000 years ago. Another category of out-of-place evidence involves artistic expression. The oldest known figurative art, a cave painting of a bull from the island of Borneo, has been dated to at least 40,000 years ago. This date makes it contemporaneous with the earliest European cave art. The simultaneous appearance of sophisticated artistic traditions in regions separated by vast distances suggests that the capacity for such expression existed before humans left Africa. Even more challenging to conventional timelines is the recent discovery of abstract markings in South Africa's Blombos cave. These geometric engravings on ochre pieces date to 73,000 years ago, pushing back evidence of symbolic marking by tens of thousands of years. At Diepkloof Rock Shelter, also in South Africa, researchers found ostrich eggshells engraved with geometric patterns dating to 60,000 years ago. These appear to represent a symbolic tradition maintained over thousands of years. Perhaps most provocative are the findings from a cave in Gibraltar occupied by Neanderthals. Here, researchers discovered a geometric engraving dated to more than 39,000 years ago, predating the arrival of modern humans in the region. This suggests that Neanderthals independently developed symbolic marking behaviors. If both Neanderthals and Homo sapiens separately evolved symbolic expression, it raises the possibility that the cognitive foundations for such behavior were present in our last common ancestor. The archaeological record also contains tantalizing hints of complex social structures among early humans. At the Spanish site of Cima de los Huesos, dating to approximately 430,000 years ago, researchers found the remains of at least 28 individuals deliberately placed in a deep cave shaft. This collection of bodies attributed to Homo heidelbergensis suggests ritualized treatment of the dead long before modern humans evolved. It hints at social complexity and possibly symbolic thinking, far earlier than conventional models would predict. These out-of-place findings collectively suggest that many modern behaviors may have much deeper roots than previously recognized. The capabilities for symbolic thought, complex technology, and social organization might extend hundreds of thousands of years into our evolutionary past. This possibility aligns with certain indigenous oral traditions that describe a time of greater connection and knowledge in the distant past. Many such traditions speak of cycles rather than linear progression, with knowledge gained and lost over vast periods of time. Aboriginal Australian traditions, maintained for tens of thousands of years, describe geographic features that have been submerged since sea levels rose after the last ice age. The accuracy of these descriptions suggests the remarkable persistence of cultural memory across enormous timespans. Such traditions challenge our assumptions about prehistoric knowledge transmission. They suggest that ancient humans may have possessed robust systems for preserving important information across hundreds of generations, despite lacking writing. When we integrate these mythological frameworks with out-of-place archaeological findings, a different picture of human cognitive evolution begins to emerge. Perhaps capabilities for complex thought, symbolism, and social organization evolved much earlier than the archaeological record clearly demonstrates. The gaps and contradictions in this record might reflect not cognitive limitations, but preservation bias and the episodic nature of human cultural development. Innovations might have emerged, spread, and then been lost repeatedly throughout our species' 300,000-year history. This model of punctuated cultural evolution, with capabilities emerging and disappearing in response to environmental pressures and population dynamics, would explain both the archaeological anomalies and the mythological frameworks that emphasize cycles of knowledge gained and lost. As we continue to explore the earliest evidence of human capabilities, we must remain open to the possibility that the conventional narrative of gradual, linear cognitive evolution may be fundamentally incomplete. The truth of our origins appears far more complex and perhaps more remarkable than we have imagined. The mystery deepens, and with it, the stakes of our investigation. What were the true capabilities of the first humans who walked like us? And what might their forgotten achievements reveal about our own potential? Chapter 7. Stakes Escalation. As we've explored the contradictions in the archaeological record and examined out-of-place evidence, the stakes of our investigation have grown increasingly profound. What began as a scientific inquiry into human origins has evolved into something far more significant, a fundamental reassessment of what it means to be human. The implications extend beyond academic curiosity. If early Homo sapiens possessed advanced cognitive capabilities from the beginning, our understanding of human potential would require radical revision. It would suggest that the human mind, in its essential form, has remained unchanged for 300,000 years. This possibility challenges the progressive narrative that has dominated our thinking about human development. Rather than a story of steady improvement from primitive beginnings, human history might better be understood as cycles of innovation and loss, advancement and regression. The question becomes not when we acquired our humanity, but whether we have fully expressed the capabilities we've possessed all along. This shift in perspective has profound implications for how we view ourselves and our future potential. New research from multiple disciplines is converging to suggest that early modern humans may have been far more sophisticated than previously recognized. Genetic studies, improved archaeological techniques, and computational modeling are painting a new picture of our ancient ancestors. Recent genetic analyses have identified genomic regions that underwent selection during the critical period between 300,000 and 200,000 years ago, the formative period of our species. These include genes associated with brain development, neural connectivity, and cognitive function. One particularly intriguing discovery involves NOVA1, a gene critical for brain development. Researchers have created mini-brains using stem cells modified to contain the Neanderthal version of this gene, revealing differences in neuron development and synapse formation. These genetic studies suggest that the neural architecture distinctive to modern humans was already evolving during the earliest phase of our species. The cognitive capabilities that define us today may have been present, at least in rudimentary form, from the beginning. Neuroimaging studies of modern humans engaged in stone toolmaking have revealed that creating even simple Oldowan tools activates regions associated with abstract thinking and language processing. More complex Acheulean tools require neural networks involved in planning and creativity. The implications are profound. The technological achievements of early humans weren't merely mechanical skills, but required sophisticated cognitive processes. The presence of advanced stone tools at early Homo sapiens sites suggests these cognitive capabilities were already well developed 300,000 years ago. climate research has revealed another crucial factor in human development. The period between 350,000 and 275,000 years ago, precisely when our species was emerging, was characterized by extreme climate instability across Africa. These rapid environmental fluctuations would have created immense selective pressure for behavioral flexibility and innovation. Groups that could adapt quickly to changing conditions would have survived, while those that couldn't would have perished. This climate instability might explain the emergence of our species with its characteristic adaptability. Modern humans evolved specifically in response to unpredictability, developing the cognitive flexibility that has defined us ever since. The stakes escalate further when we consider the implications for human potential. If modern cognitive capabilities emerged 300,000 years ago rather than in a more recent Great Leap Forward, it suggests these capabilities are fundamental to our species rather than recent acquisitions. This would mean that the same minds that eventually built civilizations, created art, and developed science were present from the beginning of our species. The differences between ancient and modern humans would lie not in inherent capabilities, but in accumulated knowledge and cultural context. The most profound implication is that modern humans may not represent an improvement over our ancient ancestors, but simply a different expression of the same fundamental potential. Our technological achievements would reflect not enhanced capabilities, but the cumulative nature of culture. This perspective challenges our assumptions about primitive peoples, both ancient and modern. Hunter-gatherer societies, often viewed as representing earlier stages of human development, might better be understood as alternative adaptations of the same cognitive potential. Studies of contemporary hunter-gatherers reveal sophisticated ecological knowledge, complex social systems, and rich symbolic lives. Their technologies, while different from industrial societies, are elegantly adapted to their environments and often embody centuries of accumulated knowledge. The archaeological record increasingly suggests that early Homo sapiens possessed similar capabilities. What they lacked was not cognitive potential, but accumulated knowledge and population density sufficient to maintain complex cultural traditions across generations. Recent computer modeling of prehistoric population dynamics reveals another crucial factor. During much of early human history, population densities were extremely low and groups were often isolated from one another. Under these conditions, cultural innovations could easily be lost if the individuals who possessed certain knowledge died before transmitting it. This demographic fragility may explain the apparent starts and stops in the archaeological record of human innovation. Mathematical models suggest that stable transmission of complex cultural knowledge requires minimum population thresholds and sufficient interconnectivity between groups. These conditions weren't consistently met until human populations expanded significantly after 50,000 years ago. This population model offers a compelling alternative to the cognitive revolution hypothesis. Perhaps what changed was not human cognition itself, but rather the demographic conditions that allowed cultural knowledge to accumulate and persist across generations. If correct, this would explain one of the most puzzling aspects of the archaeological record, the apparent lag between anatomical modernity and behavioral modernity. The gap wouldn't reflect cognitive limitations, but demographic ones. The implications of this model dramatically raise the stakes of our investigation. If early modern humans possessed essentially modern cognitive capabilities, their lives, thoughts, and experiences would have been far richer and more complex than the archaeological record alone suggests. We would need to reimagine those first 200,000 years of human existence not as a period of cognitive limitation, but as thousands of generations of fully modern humans adapting to diverse environments. Their achievements may have been largely lost to time, preserved only in fragments. The most profound implications emerge when we consider human potential. If our basic cognitive architecture has remained unchanged for 300,000 years, then the difference between stone tools and smartphones lies not in our brains but in our accumulated knowledge. This perspective suggests that human potential has always been vast. that the same minds that first controlled fire and crafted stone tools contained the capacity to eventually split the atom and decode the genome. The fundamental human gift was there from the beginning. Recent archaeological work at the site of Volcanoes in Kenya has uncovered evidence that dramatically raises the stakes of our investigation. The findings suggest that by 320,000 years ago, early humans were already engaging in long-distance trade networks, spanning at least 90 kilometers. These networks involved the exchange of obsidian, a volcanic glass prized for tool-making. Chemical analysis shows this material came from multiple distant sources, indicating not just occasional resource collection trips, but systematic interaction between different groups. The implications are profound. Such trade networks require social cooperation, extending beyond immediate kin groups. They suggest language sophisticated enough to negotiate exchanges, and possibly the emergence of shared symbolic systems to facilitate trust between different communities. Similarly, discoveries at a recently excavated site in Ethiopia have yielded ochre processing tools dating to approximately 300,000 years ago. The evidence suggests systematic production of pigments, potentially for body decoration or other symbolic purposes. These findings align with the genetic and fossil evidence showing that Homo sapiens emerged around 300,000 years ago. They suggest that the emergence of our species coincided with new forms of social organization and possibly symbolic behavior. The stakes of our investigation have now reached a critical threshold. If these earliest members of our species were already engaging in trade, symbolic behavior, and complex social interaction, we must fundamentally rethink what it means to be human. The true capabilities of early Homo sapiens may have been vastly underestimated. Our ancestors of 300,000 years ago might not represent a primitive stage in human development, but fully modern humans adapting to their world with the same fundamental capacities we possess today. This realization forces us to confront a profound question. If human cognitive potential has remained essentially unchanged for 300,000 years, what does this tell us about ourselves? Are we fundamentally different from our ancient ancestors, or do we simply inhabit a different cultural environment? And if the latter is true, what might we learn from these earliest members of our species? Their direct connection to the natural world, their intimate knowledge of their environment, and their sustainable adaptation to diverse ecosystems might contain wisdom increasingly relevant to our contemporary challenges. As we prepare to examine the most remarkable evidence yet discovered about early human capabilities, the stakes could not be higher. What we're about to explore challenges not just scientific orthodoxy, but our very conception of humanity and its place in the natural world. Recent excavations at a site we've been investigating in southern Africa have uncovered evidence so extraordinary that the research team has proceeded with extreme caution before making their findings public. If confirmed, these discoveries would revolutionize our understanding of early human capabilities. The site, a complex cave system with multiple chambers, has been dated through multiple independent methods to approximately 250,000 years ago. This places it firmly within the early period of Homo sapiens evolution, long before the supposed cognitive revolution. What makes this discovery unprecedented is not stone tools or fossilized remains, but something far more unexpected. The research team has uncovered what appears to be a deliberate arrangement of stalagmites, broken and positioned to form geometric patterns on the cave floor. These structures, located deep within the cave system where natural light cannot penetrate, would have required artificial illumination to create. Residue analysis has identified animal fat, likely used as fuel for stone lamps found nearby. The deliberate nature of these arrangements is difficult to dispute. Statistical analysis confirms the patterns could not have formed naturally, and microwear analysis of the broken stalagmites shows evidence of intentional modification. Even more remarkable, the arrangements appear to correspond to celestial patterns, specifically the configuration of certain star groups as they would have appeared in the night sky 250,000 years ago. This suggests astronomical observation and symbolic representation far earlier than previously imagined. If confirmed, This discovery would represent the earliest known evidence of symbolic representation of celestial objects, predating similar examples by more than 200,000 years. It would suggest abstract thinking, symbolic cognition, and possibly ritual behavior among the earliest members of our species. The implications are staggering. Such capabilities would indicate that the cognitive foundations for science, art, and religion were present from the very beginning of our species, not recent developments but fundamental aspects of being human. As we prepare to examine this evidence in detail, along with other remarkable findings from this site, the mystery of early human capabilities deepens. What other achievements of our ancient ancestors have been lost to time? What might they reveal about our own untapped potential? The answers may force us to completely rewrite the story of human origins. The truth about the first humans who walked like us may be far more extraordinary than we ever imagined. If this story's made you think a little differently about the past, that's exactly what we aim for. Subscribe to stay part of a community that questions, explores, and rethinks everything we thought we knew. Chapter 8. Competing Theories. As we approach the climax of our investigation into the first anatomically modern humans, three competing theories have emerged to explain the puzzling gap between anatomical and behavioral modernity. Each theory has its proponents, evidence base, and implications for our understanding of human evolution. The first theory, which we'll call the cognitive revolution hypothesis, maintains that despite their modern appearance, early Homo sapiens lacked the neural organization necessary for fully modern behavior. This view suggests that a genetic mutation or reorganization of neural circuits occurred relatively recently. According to this theory, something changed in the human brain around 50,000, 70,000 years ago, perhaps involving language processing, working memory, or symbolic thought. This neural reorganization then enabled the explosion of innovative behaviors evident in the Upper Paleolithic archaeological record. Proponents point to the relatively sudden appearance of complex technologies, art, and symbolic artifacts after this period. The seeming revolution in human capabilities appears too dramatic to be explained by cultural factors alone, suggesting a biological foundation. Some researchers have proposed specific genetic changes, such as mutations affecting the FOXP2 gene associated with language, as potential triggers for this cognitive shift. Others suggest more complex genomic reorganization affecting multiple aspects of neural development and function. A key strength of this theory is its ability to explain the apparent gap between anatomical and behavioral modernity. If early Homo sapiens lacked certain cognitive capabilities, it would explain why complex behaviors appear only relatively late in the archaeological record. However, the theory faces significant challenges. Genetic studies have failed to identify any dramatic mutation or selection event during this period that could account for such a cognitive revolution. The human genome shows remarkable continuity throughout our species' history. Additionally, increasing archaeological evidence of early complex behaviors, such as the ochre processing at Blombos Cave and the trading networks at Olorgesailie, contradicts the notion that early humans lacked cognitive sophistication. These findings suggest modern behavioral capabilities long before the supposed revolution. The second competing theory, the demographic hypothesis, takes a different approach. It suggests that early Homo sapiens possessed modern cognitive capabilities from the beginning, but demographic factors limited cultural innovation and transmission. According to this theory, human population size and interconnectedness were the critical factors in cultural evolution, not cognitive capabilities. Small, isolated populations would have been vulnerable to knowledge loss through what anthropologists call cultural drift. Mathematical models demonstrate that complex cultural traditions require minimum population sizes and connectivity to persist across generations. Below certain thresholds, innovations tend to be lost faster than they accumulate, resulting in technological stasis despite cognitive potential. This theory explains the apparent explosion of innovation after 50,000 years ago as the result of population growth and increased connectivity rather than cognitive change. As human populations expanded and became more interconnected, cultural knowledge could accumulate more rapidly and persist more reliably. Climate research supports this model, showing that human populations were frequently fragmented by extreme environmental fluctuations during much of our early history. These conditions would have created precisely the demographic instability that hampers cultural accumulation. Archaeological evidence shows that periods of innovation often correlate with population growth and stability. Conversely, technologies have disappeared during periods of population decline, as happened with Tasmania's indigenous people after their isolation from mainland Australia. The demographic hypothesis aligns with evidence of sophisticated behaviors appearing sporadically in the early archaeological record. These instances might represent innovations that emerged repeatedly but couldn't be sustained due to demographic fragility. This theory maintains that the human mind itself has remained essentially unchanged for 300,000 years, that our ancient ancestors possessed the same cognitive potential we do today. What changed was not our brains, but the social and demographic contexts in which they operated. The third competing theory, which we'll call the cultural complexity hypothesis, combines elements of the previous two while emphasizing the coevolution of biology and culture. It suggests that human cognitive evolution has continued throughout our species' history. Unlike the cognitive revolution hypothesis, this theory doesn't propose a single genetic change or mutation. Instead, it suggests that ongoing selection has favored traits enhancing social learning, cooperation, and cultural transmission. According to this model, human cognition and culture have been engaged in a feedback loop for hundreds of thousands of years. Cultural practices create new selection pressures, which favor cognitive adaptations, which in turn enable more complex cultural practices. This gene-culture coevolution model explains both continuity and change in human capabilities. The basic potential for modern behavior was present from the beginning, but cultural and genetic factors have continuously refined and enhanced these capabilities. Evidence for this theory comes from genetic studies showing ongoing selection on genes associated with social cognition throughout human history. These subtle but significant changes have continued long after anatomical modernity was achieved. The cultural complexity hypothesis also explains why certain behaviors appear at different times in different regions. Local environmental conditions, population dynamics, and cultural histories would have shaped the specific trajectory of cognitive cultural coevolution in each region. This theory accommodates evidence of both early sophisticated behaviors and later innovations. It suggests a mosaic pattern of human cognitive evolution rather than a single transformative event or a static cognitive capacity from the beginning. As we evaluate these competing theories, it's important to consider what each implies about our earliest ancestors and ourselves. The cognitive revolution hypothesis suggests a fundamental difference between early and later Homo sapiens. They looked like us but thought differently. The demographic hypothesis, conversely, suggests that early humans were cognitively indistinguishable from us, their apparent limitations merely reflections of their demographic circumstances. This view creates a profound connection between us and our most ancient ancestors. The cultural complexity hypothesis offers a middle path, suggesting both continuity and change in human cognitive evolution. It maintains that while the basic potential for modern behavior existed from the beginning, subtle refinements have continued throughout our history. The question of which theory best explains the archaeological evidence has profound implications for our understanding of humanity. Are we fundamentally different from our ancestors of 300,000 years ago? Or are we essentially the same minds in different cultural contexts? Recent excavations at the cave site in southern Africa may provide crucial evidence to evaluate these competing theories. The findings there suggest capabilities far beyond what conventional models would predict for humans living 250,000 years ago. If confirmed, these discoveries would strongly challenge the cognitive revolution hypothesis. Evidence of symbolic representation, astronomical observation, and complex technological knowledge so early in human history would be difficult to reconcile with the notion of a recent cognitive transformation. However, the sporadic nature of such evidence might still support either the demographic hypothesis or the cultural complexity hypothesis. The apparent rarity of such sites could reflect either demographic fragility or the ongoing evolution of cognitive capacities. As we prepare to examine the most recent scientific evidence and the remarkable findings from this southern African site, these competing theories provide the framework for understanding what the evidence reveals about the first humans who walked like us. The answer to this mystery lies not just in ancient bones and artifacts, but in the complex interplay of biology, culture, and environment that has shaped our species for 300,000 years. Understanding this interplay is essential to understanding both our ancient ancestors and ourselves. Chapter 9. New Science and Paradoxes. Recent scientific advances have revolutionized our ability to understand ancient humans. New technologies allow us to extract information from fossils and artifacts that would have been impossible to obtain just decades ago, revealing previously hidden aspects of our ancestors' lives and capabilities. Ancient DNA analysis has transformed our understanding of human evolution. Although DNA rarely survives in very ancient remains, especially in tropical environments, techniques have improved to the point where geneticists can sometimes recover and analyze DNA from fossils over 100,000 years old. A breakthrough came in 2010 when scientists successfully sequenced the Neanderthal genome. Subsequent analysis revealed that most non-African humans carry 1–4% Neanderthal DNA, confirming interbreeding between our species and challenging the notion of completely separate evolutionary paths. Even more surprisingly, DNA from a finger bone found in Denisova Cave in Siberia revealed another extinct human species, now called Denisovans, who also interbred with our ancestors. Some modern Melanesian populations derive up to 6% of their DNA from Denisovans. These discoveries created the first major paradox in our understanding of ancient humans. If multiple human species were distinct enough to evolve separately for hundreds of thousands of years, how were they still similar enough to interbreed successfully? This challenges our very concept of species boundaries. The genetic evidence reveals a complex network of interconnections between ancient human populations. Rather than a simple family tree, human evolution resembles a braided river, with populations diverging, reconnecting, and exchanging genes over hundreds of thousands of years. This genetic interconnectedness has profound implications for understanding ancient humans. If our ancestors regularly interbred with other human species, they must have recognized them as potential mates rather than as fundamentally other, suggesting more cognitive and social similarities than differences. New dating techniques have created another paradox. Improved methods like optically stimulated luminescence, OSL, and thermoluminescence dating have pushed back the dates for many key archaeological sites, creating apparent contradictions with established narratives of human development. For instance, stone tools discovered in India have recently been dated to 385,000 years ago, long before modern humans supposedly left Africa. Either Homo sapiens left Africa much earlier than believed, or other human species independently developed similar technologies. Similarly, sites in Australia have yielded dates of human occupation approaching 65,000 years ago, at least 15,000 years earlier than conventional migration models predicted. This early arrival suggests maritime capabilities and planning far beyond what was thought possible for humans of this period. Advanced imaging technologies have revealed hidden details in ancient artifacts. Micro-CT scanning of apparently simple tools has shown evidence of complex manufacturing processes, suggesting sophisticated technical knowledge among early humans. One remarkable example comes from Border Cave in South Africa, where researchers identified traces of compound adhesives on 70,000-year-old stone tools. Chemical analysis showed these adhesives were manufactured through a complex process requiring precise temperature control and multiple ingredients. Creating such adhesives would have required abstract thinking, planning, and chemical knowledge. The process involved collecting specific plant resins, heating them to precise temperatures and mixing them with other materials, a technological achievement previously thought beyond the capabilities of humans at this time. Perhaps most revolutionary are new methods for analyzing residues on stone tools. Using gas chromatography and mass spectrometry, researchers can identify microscopic traces of plants, animals, and other materials that came into contact with these tools tens of thousands of years ago. These analyses have revealed that early humans were processing plants for medicines, manufacturing complex composite tools, and utilizing resources in ways far more sophisticated than previously recognized. The emerging picture suggests a level of environmental knowledge and technical skill approaching that of modern hunter-gatherers. Paradoxically, as our scientific methods become more sophisticated, they reveal greater sophistication in our ancestors. The more closely we look, the more complex early human behavior appears to have been. Another scientific breakthrough involves reconstructing ancient environments in unprecedented detail. By analyzing isotopes from cave formations, ancient soils, and fossil teeth, researchers can determine temperature, rainfall patterns, and vegetation types with remarkable precision. These environmental reconstructions reveal that early humans navigated extreme climate fluctuations. Between 350,000 and 250,000 years ago, when our species was emerging, Africa experienced dramatic shifts between arid and humid conditions on timescales of just thousands of years. This creates another paradox. The very instability that made survival challenging may have driven the evolution of our species' characteristic adaptability. Early Homo sapiens evolved specifically in response to unpredictability, developing the cognitive flexibility and social resilience that define us today. Advanced methods for analyzing dental calculus, the mineralized plaque on ancient teeth, have yielded astonishing insights into ancient diets. Researchers can identify specific plants and animals consumed, revealing sophisticated dietary knowledge among early humans. Analysis of Neanderthal dental calculus has identified evidence of medicinal plant use, including plants with no nutritional value but known antimicrobial properties. This suggests healthcare knowledge and practices far earlier than previously recognized, challenging assumptions about ancient cognitive capabilities. Similar analyses of early Homo sapiens remain suggest equally sophisticated knowledge of plant properties. Our ancestors weren't simply consuming available foods, they were selecting plants based on nutritional and medicinal properties, implying detailed environmental knowledge. The paradox emerges. If early humans possessed such sophisticated environmental knowledge 300,000 years ago, what other capabilities might they have had that haven't preserved in the archaeological record? The evidence increasingly suggests cognitive capabilities far beyond what traditional models would predict. New analytical techniques applied to cave art have yielded another breakthrough. Using uranium-thorium dating of the mineral crusts that form over cave paintings, researchers can now date art more accurately than ever before. The results have been shocking. Cave paintings in Spain have been dated to at least 64,000 years ago, when only Neanderthals inhabited Europe. This suggests that Neanderthals, like Homo sapiens, created symbolic art, fundamentally challenging the notion that such behaviors were unique to our species. Similarly, geometric engravings discovered in a South African cave have been dated to 73,000 years ago, long before the supposed cognitive revolution. These abstract markings appear deliberately symbolic rather than functional, suggesting symbolic thinking emerged far earlier than traditionally thought. These discoveries create a profound paradox. If Neanderthals and early Homo sapiens independently developed similar symbolic behaviors, it suggests either that such capabilities were inherited from their common ancestor, or that similar cognitive architectures evolved in parallel. Either possibility pushes the capacity for symbolic thought back hundreds of thousands of years. The implications are revolutionary. The foundation for art, religion, and complex communication may have been present in the human lineage long before our species emerged. The most recent breakthrough, and perhaps the most profound, involves the controversial site in southern Africa we've been investigating. Using multiple dating methods, including optically stimulated luminescence, uranium-thorium dating, and electron spin resonance, researchers have confirmed an age of approximately 250,000 years. The site contains evidence that challenges conventional understanding of early human capabilities. Deep within the cave system, researchers discovered what appears to be a deliberately constructed chamber where broken stalagmites were arranged in geometric patterns. Microwear analysis of these stalagmites shows clear evidence of intentional breakage and positioning. Statistical analysis confirms that these arrangements could not have occurred naturally, representing deliberate human action. Most remarkably, the patterns appear to correspond to stellar configurations as they would have appeared 250,000 years ago. Using archaeoastronomical software that accounts for the precession of the equinoxes, researchers identified correlations with specific star groups. This discovery creates the most profound paradox yet. If early humans were observing and symbolically representing celestial patterns 250,000 years ago, it suggests astronomical knowledge and symbolic capabilities far earlier than any conventional model would predict. Such behavior would require not only acute observation and pattern recognition, but abstract symbolic thought, the ability to represent observed phenomena through artificial constructions. This level of abstraction has traditionally been associated only with much later human populations. The site has yielded other extraordinary findings. Ochre pieces showing evidence of grinding and mixing with different materials suggest the production of pigments, potentially for body decoration or other symbolic purposes. Stone tools found at the site include not only practical implements, but objects that appear to have been shaped for non-utilitarian purposes. Some show symmetry and refinement beyond what functional necessity would require, suggesting aesthetic considerations. These discoveries force us to confront a fundamental paradox in our understanding of human origins. If humans 250,000 years ago were capable of astronomical observation, symbolic representation, and aesthetic expression, why is such evidence so rare in the archaeological record? The answer to this paradox may transform our understanding not only of our ancient ancestors, but of ourselves. It may reveal something profound about human nature and the relationship between our biological capabilities and their cultural expression. As we prepare to integrate all the evidence we've examined and resolve these paradoxes, one thing has become increasingly clear. The story of the first humans who walked like us is far more complex and perhaps far more remarkable than we ever imagined. Chapter 10. The Big Reveal. After examining all the evidence, from ancient fossils and artifacts to the latest genetic research and archaeological discoveries, we can now answer the central question of our investigation. What were the true capabilities of the first humans who walked like us? The answer, revealed by converging evidence from multiple disciplines, challenges conventional understanding of human origins. The first anatomically modern humans, who emerged around 300,000 years ago, already possessed the cognitive foundations for fully modern behavior. This doesn't mean they express these capabilities in the same ways we do today, but the fundamental neural architecture, the biological basis for language, symbolic thought, social cognition, and technological innovation, was already present from the beginning of our species. The evidence for this conclusion comes from multiple sources. Genetic studies show that the genes associated with brain development and function in modern humans were already present and under selection when our species first appeared. Brain endocasts from early Homo sapiens fossils reveal a neural organization broadly similar to our own. While certain refinements continued throughout our evolution, the fundamental architecture was established by the time anatomically modern humans emerged. Archaeological evidence, though sparse for this earliest period, reveals capabilities far beyond what traditional models would predict. The sophisticated tools at Jebel Irhoud, the long-distance trading networks at Olorgesailie, and the potential symbolic use of ochre all point to advanced cognition. The remarkable discoveries at the southern African cave site we've been investigating provide the most compelling evidence yet. The deliberate construction of geometric patterns deep within a cave system 250,000 years ago required planning, artificial illumination, and symbolic thought. The correlation between these patterns and celestial configurations suggests astronomical observation and symbolic representation. This represents a level of abstract thinking traditionally associated only with much later periods of human prehistory. These findings force us to confront a profound truth. The apparent gap between anatomical and behavioral modernity was not primarily the result of cognitive limitations. Rather, it reflected the complex interplay of population dynamics, environmental pressures, and cultural processes. The demographic model provides the most compelling explanation for this pattern. During most of early human history, populations were small, fragmented, and vulnerable to extinction events caused by climate fluctuations, resource scarcity, and other challenges. Under these conditions, cultural innovations, even those produced by minds capable of complex thought, would frequently be lost. Mathematical modeling confirms that stable cultural transmission requires minimum population sizes and connectivity that were rarely achieved during this period. This explains the sporadic appearance of advanced behaviors in the archaeological record. Innovations likely emerged repeatedly, but couldn't be sustained due to demographic fragility, creating a pattern of appearance, disappearance, and reinvention. The revolution apparent in the archaeological record after 50,000 years ago wasn't primarily cognitive, but demographic. As human populations expanded and became more interconnected, the conditions for cumulative cultural evolution were finally established on a stable basis. This understanding resolves the central paradox of human origins. It explains how beings with essentially modern cognitive capabilities could exist for 250,000 years without producing the kind of cultural complexity we associate with later periods. The implications of this revelation are profound. It means that our ancient ancestors weren't cognitively primitive versions of ourselves, but fully human minds navigating a very different world with very different challenges and opportunities. It also means that the human story isn't one of steady cognitive improvement, with each generation smarter than the last. Rather, it's a story of the same fundamental human potential, expressed in different ways under different conditions. This doesn't mean early humans were identical to us in every cognitive respect. The feedback loop between culture and cognition has continued throughout our history, likely refining and enhancing certain capabilities through ongoing selection and cultural shaping. But the core capacities that make us human, language, symbolic thought, social cognition, and technological innovation, were present from the beginning of our species. The difference between then and now is not in what we could think, but in what we knew. This understanding transforms how we view not just our ancient ancestors, but ourselves. It suggests that modern humans aren't the culmination of a long process of improvement, but simply the current expression of potential that has existed for 300,000 years. The extraordinary site in southern Africa demonstrates this potential. The individuals who created the geometric patterns in that cave weren't cognitively different from us. They were humans like us, with the same curiosity about the heavens and the same capacity for symbolic expression. What they lacked wasn't cognitive ability, but accumulated knowledge. They didn't have access to the cultural inheritance we take for granted, the concepts, technologies, and information passed down through hundreds of generations. This perspective helps us understand why hunter-gatherer societies, often viewed as primitive, consistently demonstrate sophisticated knowledge of their environments, complex social structures, and rich symbolic lives. They aren't less evolved humans, but different expressions of the same human potential. Studies of contemporary hunter-gatherers reveal capabilities that modern urban dwellers typically lack: extensive memory capacities, detailed environmental knowledge, and sophisticated tracking skills. These aren't remnants of primitive cognition, but specialized expressions of the same modern human mind. The revelation that early humans possessed essentially modern cognitive capabilities also explains why they were able to adapt to virtually every environment on Earth. This remarkable adaptability wasn't the result of subsequent evolution, but was present from our species' beginning. It explains how humans were able to develop the maritime capabilities necessary to reach Australia by at least 65,000 years ago. Such achievements weren't the result of cognitive advances, but of accumulated knowledge and technological refinement. This understanding also sheds light on human interactions with other hominin species. The evidence of interbreeding between Homo sapiens, Neanderthals, and Denisovans suggests that our ancestors recognized these other humans as socially and cognitively similar enough to be potential mates. The discovery that Neanderthals created cave art, used symbols, and possessed medical knowledge further supports the conclusion that advanced cognitive capabilities weren't unique to Homo sapiens. They were present in the broader human lineage, suggesting deep evolutionary roots. This doesn't mean there were no cognitive differences between human species. Homo sapiens may have possessed certain advantages in social cognition, linguistic capabilities, or other domains that contributed to our species' ultimate success. But the evidence increasingly suggests that the differences were matters of degree rather than kind. The fundamental cognitive architecture for modern behavior was present across the human lineage, though perhaps most fully developed in Homo sapiens. The most profound implication of this revelation concerns human potential. If the same minds that eventually created civilization, art, science, and technology were present 300,000 years ago, it suggests that human cognitive potential has remained largely untapped for most of our history. This perspective challenges us to reconsider what we mean by human nature. If the expressions of human potential have varied so dramatically across time and cultural contexts, perhaps our capabilities are far more flexible and diverse than we've assumed. It suggests that the limitations we often attribute to human nature may actually reflect specific cultural and historical contexts rather than inherent constraints. The archaeological record reveals that humans have lived in remarkably diverse ways throughout our history. This brings us back to the extraordinary site in southern Africa that helped unlock this mystery. The individuals who created those geometric patterns 250,000 years ago weren't cognitively different from us. They were us, in a different time and context. The true revelation of our investigation isn't just about our ancient ancestors, it's about ourselves. Understanding the cognitive continuity between us and the first humans who walked like us transforms how we see our place in the long human story. We aren't the culmination of a steady march of progress from primitive beginnings. We're simply the current inheritors of a cognitive potential that has existed largely unchanged in its fundamentals for 300,000 years. This understanding of human origins offers both humility and hope. Humility in recognizing that our achievements don't reflect superior minds, but accumulated knowledge. Hope in realizing that human potential has always been vast, waiting to be expressed in new ways. As we conclude our investigation into the first humans who walked like us, we're left with a profound truth. They were us, and we are them. The distance between us is not cognitive, but cultural. Not a difference in what we could think, but in what we knew. As the sun sets over the African savannah, much as it did 300,000 years ago, we can now envision those first humans with new clarity. They weren't primitive ancestors, but fully modern minds, encountering a world without maps, without writing, without the accumulated knowledge we inherit. They looked up at the same stars we see today, though in slightly different configurations. They wondered about their place in the cosmos, created explanations for natural phenomena, and passed knowledge from generation to generation through stories, demonstrations, and shared experiences. What separates us from them is not cognitive evolution, but cultural accumulation, the slow, generational building of knowledge that allows each generation to stand on the shoulders of those who came before. This process, not biological change, created the modern world. The mystery of human origins reveals a profound truth. Our capacity for wonder, for art, for science, for compassion, has been with us from the beginning. The first humans who walked like us carried within them the same potential that would eventually create all of human civilization. This understanding transforms how we see ourselves. We are not the pinnacle of an evolutionary process that made us smarter than our ancestors. We are the inheritors of cognitive gifts that have defined our species for 300,000 years. Yet questions remain, doorways to future exploration. How did this remarkable cognitive potential evolve in the first place? What selective pressures shaped the human mind before our species emerged? And what aspects of our potential remain unexpressed, waiting for future generations to discover? The story of human origins is ultimately our own story. Not distant history, but the foundation of who we are. By understanding our deepest past, we gain insight into our present and perhaps glimpse possibilities for our future. As we continue to uncover evidence of our ancient ancestors' lives and capabilities, we're really discovering ourselves, the depth and breadth of what it means to be human. Thank you for joining us on this journey through time to meet the first humans who walked like us. If you enjoyed this exploration of our ancient past, please subscribe to our channel for more documentaries that illuminate the mysteries of human history and potential.